In 2025, Arizona is turning the desert into a construction war zone of epic proportions. From billion-dollar highways to futuristic transportation networks, these megaprojects are on a scale the state has never seen before. Let's uncover the massive builds transforming Arizona and why this state will soon be at the forefront of the American construction industry. In the heart of the Sonoran Desert, the expansion of Phoenix's Valley Metro Rail into the South Central Corridor stands as a testament to integrated urban infrastructure and the challenges of building transit lines within an active metropolitan grid. The South Central Extension represents a critical upgrade to the region's transportation network, stretching over 5 miles in length and connecting downtown Phoenix to the underserved communities along South Central Avenue. From the earliest planning phases, engineers and construction teams faced numerous logistical and technical hurdles that required careful orchestration and innovation. The initial phase involved comprehensive subsurface utility engineering. Before any excavation could begin, teams deployed ground-penetrating radar and vacuum excavation to identify and map buried utilities such as gas mains, water lines, electrical conduits, and fiber optic cables. These utilities needed to be either protected in place or relocated entirely. Once mapping was complete, utility relocation began in phases to avoid service disruptions to residents and businesses. Concurrently, crews worked to establish temporary traffic control measures to maintain access along South Central Avenue, a heavily traveled arterial road. Site grading and roadbed preparation came next. Earthwork involved removing existing pavement and regrading to establish subgrade elevations that aligned with the future track alignment. Stormwater management posed a unique challenge due to the region's susceptibility to flash flooding. Civil engineers incorporated a network of underground drainage structures and retention basins designed to intercept and detain stormwater runoff, particularly around intersections and low-lying zones. Track installation commenced with the precise layout of the guideway. Using laser surveying and GPS-based control points, the track center line was marked, and crews began excavation for the ballastless track slab foundation. A reinforced concrete slab was poured in segments, followed by placement of embedded direct fixation fasteners to hold the rail in position. Continuous welded rail was delivered in long lengths and thermite welded on site to ensure a seamless, low-maintenance riding surface. Alignment tolerances were kept within strict specifications using precision jigs and hydraulic rail positioners. Simultaneously, construction of the traction power substations and overhead catenary system advanced. The substations, spaced strategically along the corridor, required deep foundations and high-voltage switchgear installations. Overhead contact system poles were erected using truck-mounted augers and cranes, and tensioned copper contact wire was strung in sections, later adjusted for sag and alignment. The system included automatic tensioning devices to account for thermal expansion in the desert heat. Station construction featured reinforced concrete platforms built to accessibility standards, with integrated canopy structures providing shade and shelter. Each station was equipped with passenger information systems, fare vending machines, lighting, and public art elements designed in coordination with local artists. Landscaping utilized drought-tolerant plantings and drip irrigation to align with regional sustainability goals. The project also included new signalized intersections and traffic signal priority systems, enabling trains to move through cross streets efficiently. Roadway reconstruction, including new pavement, sidewalks, and bike lanes, was integrated into the final phases to ensure multimodal connectivity. Throughout the build, community outreach and phased construction scheduling played a vital role in minimizing disruptions and maintaining stakeholder support. The South Central Extension ultimately reinforced the importance of equitable transit access and showcased the complexities involved in urban light rail construction within an established city framework. One of the most ambitious freeway improvement undertakings in the Phoenix metropolitan area is the Arizona Department of Transportation's Broadway Curve project, which targets a congested segment of Interstate 10. This stretch, encompassing roughly 11 miles from Interstate 17 to Loop 202, serves as a crucial artery for both commuter and freight traffic. Given the region's rapid population growth and increasing traffic volumes, the reconstruction and widening of the Broadway Curve was designed to significantly boost capacity, reduce travel time, and enhance overall safety. The project commenced with a detailed phase of geotechnical investigations and environmental clearances. Borehole drilling and soil sampling were carried out across the corridor to assess bearing capacity, subsurface conditions, and groundwater levels. These findings informed the design of retaining walls, bridge foundations, and pavement sections. Early coordination with utility companies was critical, as the corridor housed numerous high-voltage electrical lines, sewer mains, water lines, and telecommunications conduits. Each utility conflict had to be resolved through relocation or protective measures prior to major excavation activities. Construction began with the expansion of the freeway's footprint, which required significant demolition of existing infrastructure. This included the removal of aging sound walls, bridge decks, and portions of the roadway itself. To manage dust and minimize particulate emissions during demolition, crews utilized water spraying systems and mounted mist cannons. Excavated materials were sorted on site, with recyclable concrete and asphalt diverted for reuse in base courses or temporary detours. One of the project's signature features was the addition of new travel lanes and high-occupancy vehicle lanes in both directions. To accommodate this, the freeway's subgrade had to be widened, involving large-scale, earth-moving operations using scrapers, bulldozers, and graders. Where right-of-way was constrained, mechanically stabilized, earth-retaining walls were employed, with precast concrete panel facings and geogrid reinforcements layered within compacted backfill. Bridge construction was another critical aspect. Several interchanges and overpasses, including those at Broadway Road and State Route 143, were either reconstructed or newly built. Foundations were formed using cast-in drilled hole piles, and superstructures were assembled with precast concrete girders hoisted into place using hydraulic cranes during overnight closures. Concrete bridge decks were poured with embedded post-tensioning ducts to handle long-span stresses and reduce deflection. Pavement design for the mainline lanes relied on a composite structure of crushed aggregate base and Portland cement concrete chosen for its durability under heavy truck loads. Stringline-guided slip-form paving machines ensured precise elevation and cross-slope. Adjacent auxiliary lanes and ramps used hot mix asphalt with polymer-modified binders for added flexibility under thermal cycling. In parallel, new drainage systems were installed, featuring large-diameter, reinforced concrete pipes, catch basins, and retention basins to manage the significant runoff generated by impervious surfaces. Intelligent transportation systems were also embedded, including dynamic message signs, traffic detection loops, and closed-circuit television cameras, all linked to ADOT's Traffic Operations Center. Rising from the heart of downtown Phoenix, the Central Station East and West Towers represent a complex integration of vertical development and urban transit infrastructure. Constructed atop and adjacent to the existing Phoenix Transit Hub, these mixed-use high-rises demanded an extraordinary level of coordination between structural engineering, architectural planning, and transportation logistics. The project's objective was to transform the site into a dense, transit-oriented development that includes residential, commercial, and public amenities while maintaining uninterrupted operation of the Central Station bus and light rail services throughout construction. The first phase involved site mobilization and deep foundation work. Because the towers were to be built atop an active bus terminal, extensive structural analysis was undertaken to determine load distribution and minimize any impacts to the operational platform below. Engineers opted for a mat foundation design for both towers, reinforced with a dense grid of drilled shafts extending over 100 feet deep into competent strata. These shafts, filled with high-strength concrete and steel rebar cages, provided the vertical support necessary for the tower's substantial loads. A temporary shoring and decking system was installed above the transit level, creating a working platform that allowed construction to proceed while preserving bus operations below. This system included structural steel beams supported by temporary columns, enabling the casting of ground-level slabs without impeding passenger movement or vehicle flow. Noise and vibration controls, including insulated barriers and work hour restrictions, were implemented to maintain the comfort and safety of transit users during critical operations like pile driving and concrete placement. Once the foundation systems were completed, vertical construction commenced using a central concrete core methodology. The core, housing elevators, stairwells, and utility risers, was formed using a self-climbing formwork system that allowed rapid upward progress while maintaining strict vertical tolerances. Simultaneously, post-tensioned concrete floor plates were constructed in successive lifts, with crews pouring and tensioning each level on a 5 to 7 day cycle. Structural columns around the perimeter were also cast in situ, reinforced with high-density steel cages to accommodate wind and seismic loads typical of high-rise structures. Mechanical, electrical, and plumbing systems were integrated into each floor plate through a coordinated building information modeling process, which allowed conflicts to be resolved before installation. Dedicated mechanical floors were spaced periodically throughout the tower to house air handling units, water booster pumps, and electrical switchgear, with vertical shafts providing routing for all distribution systems. The tower's facades combined high-performance glazing and curtain wall systems with architectural shading devices. Installation was carried out using tower cranes and swing stage scaffolding, with prefabricated curtain wall panels hoisted and anchored to embedded plates in the concrete structure. These facade systems were designed to meet energy efficiency codes and acoustic performance standards, given the site's proximity to active rail lines and bus traffic. On completion, the central station, east and west towers offered a blend of residential units, retail space, and public areas, all directly integrated with the city's transit network. The successful execution of the project demonstrated how complex high-rise construction can coexist with critical public infrastructure through meticulous planning, staged implementation, and precision engineering. Tucked within the expanding industrial corridors of the Phoenix metropolitan area, the development of Mack Innovation Park marks a significant addition to Arizona's logistics and advanced manufacturing infrastructure. Conceived as a high-capacity, master-planned industrial complex, this project demanded extensive land preparation, high-performance building construction, and strategic utility coordination to accommodate a range of high-tech tenants and warehousing operations. The entire endeavor had to balance rapid deployment schedules with strict technical and environmental requirements, especially given the scale of build-out across hundreds of acres. Initial groundwork began with site clearing, grading, and soil stabilization. Given the arid climate and typically sandy soils of the region, crews employed compaction and cement-treated base layers to ensure stable subgrades. Laser-guided grading equipment shaped the landscape according to precise elevation tolerances, enabling future buildings to maintain proper drainage and prevent settlement. In areas with expansive clays or other problematic soils, lime treatment was used to improve load-bearing capacity and minimize heave potential. Utility installation came next, and involved major trenching operations to lay out an underground network for stormwater, sewer, potable water, reclaimed water, and fire suppression systems. Due to the park's high energy demand projections, the electrical infrastructure included large-scale conduit banks and dual-feed substations designed to deliver redundancy and reliability. Telecommunications infrastructure was also embedded at an early phase, with fiber optic backbones laid in parallel to power ducts to serve future tenants with high-speed connectivity. With infrastructure in place, building construction moved forward on multiple fronts, often with overlapping phases across the expansive site. The warehouse and advanced manufacturing structures typically featured tilt-up concrete panel walls, chosen for their speed of construction and cost efficiency. These panels were cast horizontally on-site, reinforced with steel rebar, and lifted into position using hydraulic cranes. After alignment and bracing, they were welded to embedded plates in the foundation and tied together with structural steel roof systems. Roof systems for these buildings incorporated long-span steel joists and mechanically fastened TPO membrane roofing, which offered durability and reflectivity in Arizona's intense sunlight. Several buildings included clear-story glazing and rooftop HVAC units mounted on steel platforms, allowing for flexible interior space configurations without ground-level obstructions. Interior fit-outs were designed to accommodate a wide range of tenant uses, from light manufacturing to distribution and research activities. This flexibility was achieved through wide column spacing, high clear heights, and heavy-duty floor slabs designed for forklift traffic and equipment loads. Electrical and mechanical systems were installed with scalability in mind, including transformer vaults, backup generator pads, and chilled water loops in select areas. Site development was completed with extensive truck courts, dock-high loading bays, and auto parking lots constructed of reinforced concrete and asphalt pavements. Landscaping used xeriscape principles, combining native desert plants with efficient drip irrigation systems to reduce water consumption. Site lighting utilized LED fixtures mounted on steel poles with photocell and motion control systems to reduce energy usage during off-peak hours. Mack Innovation Park stands as a prime example of contemporary industrial development tailored for versatility, efficiency, and rapid tenant deployment. The project reflects the growing demand for scalable, infrastructure-rich environments capable of supporting Arizona's evolving economic landscape. In the western reaches of the Phoenix metropolitan area, the construction of Buc-ee's in Goodyear, Arizona, introduced a uniquely large-scale convenience and fueling center to the southwest. Known nationally for its sprawling facilities and extensive amenities, building a Buc-ee's location required coordination across civil, structural, mechanical, and traffic engineering disciplines. The Goodyear site posed specific challenges related to site access, utility capacity, and the sheer size of the development, which spans tens of thousands of square feet under roof and includes well over 100 fuel pumps. Construction began with site acquisition and preparation on a parcel of land located near a high-traffic interstate interchange. Grading and earthwork were extensive, as the natural topography included uneven terrain and drainage channels that needed to be recontoured. Bulldozers and graders worked in tandem with GPS-guided systems to establish flat pads for the main building, fuel canopy, and ancillary structures, while engineered fills and retention basins were shaped to manage stormwater runoff and comply with local drainage ordinances. Installation of utilities was an early priority. Buc-ee's facilities demand significant electrical and water service to support lighting, refrigeration, HVAC, restrooms, car wash systems, and commercial kitchen operations. Multiple utility corridors were trenched and installed in parallel, with electrical conduits, sewer mains, and domestic water lines placed in pre-engineered routes. Electrical service included pad-mounted transformers and switchgear designed to handle peak loads with backup circuits for critical systems. A dedicated fire suppression loop with underground hydrants and backflow prevention was installed to serve both the retail building and fueling areas. The main structure was constructed using a combination of steel framing and reinforced masonry. Structural steel columns and open web joists form the building's skeleton, supporting a metal roof deck over which rigid insulation and membrane roofing were applied. Masonry walls, reinforced with vertical rebar and grout-filled cores, provided lateral stability and durability against thermal expansion in the desert climate. High-performance glazing and insulation systems were used to meet energy codes and reduce cooling loads in the expansive interior. Fueling infrastructure represented a major component of the build. Underground storage tanks were installed in concrete-lined excavations with leak detection and vapor recovery systems. These tanks, some with capacities exceeding 30,000 gallons, required anchoring systems to prevent flotation due to potential groundwater intrusion. Fuel lines were routed from the tanks to the dispensing stations using flexible double-walled piping encased in protective sleeves. Above each fueling island, the steel canopy was erected with integrated lighting, signage, and fire suppression nozzles. Interior build-out included extensive plumbing, food service equipment installation, and climate control systems. The building's layout was optimized for high customer throughput, with wide aisles, durable epoxy flooring, and stainless steel fixtures. HVAC systems were zoned and included large rooftop units controlled by a centralized building automation system to maintain efficiency. Finally, site access improvements were constructed, including new turn lanes, deceleration lanes, and signalized intersections to manage the high volumes of passenger and delivery vehicle traffic. Parking lots and access roads were paved with reinforced concrete in high traffic areas and asphalt in general zones. The Buc-ee's Goodyear project demonstrated how meticulous planning and large-scale construction techniques come together to create a retail destination engineered for efficiency, resilience, and customer capacity. Some transportation corridors evolved from long-range planning models into fully realized infrastructure only after extensive engineering, environmental, and political groundwork. Arizona State Route 505 followed such a trajectory, conceptualized to serve as a critical connector within the state's expanding highway network. Designed to link developing suburban zones with major interstate corridors, the highway's construction presented a variety of technical and logistical complexities due to its alignment through mixed-use areas, including undeveloped land, residential communities, and light industrial zones. Site development for State Route 505 began with comprehensive right-of-way acquisition and environmental compliance measures. Land surveys were followed by extensive geotechnical borings to assess soil composition, moisture content, and bearing capacities. These tests identified areas where the subgrade required stabilization, particularly in floodplain-adjacent sections where clay-rich soils had the potential for seasonal swelling. To address this, engineers specified lime stabilization and geotextile reinforcements beneath the roadbed to distribute loads and maintain long-term performance. Clearing and grubbing operations removed vegetation and surface obstructions, while sediment control measures such as silt fencing and stormwater inlet protections were installed to meet environmental permitting requirements. The highway's profile grade was established using precision GPS-enabled dozers and graders, ensuring proper slope for drainage and vehicular safety. Embankment fills were compacted in lifts using vibratory rollers, and settlement monitoring devices were embedded in critical zones to track ground movement over time. Pavement structure for State Route 505 was built to accommodate projected heavy truck traffic. The typical cross-section consisted of a thick aggregate base course over which hot mix asphalt was placed in multiple lifts. In higher stress areas, such as intersections and climbing lanes, polymer-modified asphalt was specified to increase rut resistance and fatigue life. Longitudinal and transverse joints were sealed with bituminous compounds to prevent water infiltration. Interchanges along the corridor featured modern diamond and single-point urban interchange designs, depending on traffic volumes and right-of-way constraints. These interchanges required deep excavation for underpasses and extensive use of mechanically stabilized earth walls, which were constructed using alternating layers of compacted fill and steel or polymer reinforcement grids. Bridge structures utilized precast, pre-stressed concrete girders supported on drilled shaft foundations with abutments integrated into the retaining wall systems for space efficiency. Intelligent transportation systems were embedded throughout the corridor, including ramp metering systems, overhead dynamic message signs, traffic detection sensors, and fiber optic communication lines linked to regional traffic management centers. Roadside infrastructure included LED lighting mounted on galvanized steel poles, breakaway sign supports, and crash attenuators placed at key impact points to enhance roadside safety. Drainage infrastructure was extensive, consisting of reinforced concrete pipe networks, box culverts, and bioswales designed to control stormwater runoff. These systems were modeled to accommodate 100-year storm events, with detention basins strategically located to manage peak flows without overburdening downstream channels. Upon completion, State Route 505 provided not only an essential transportation corridor for central Arizona, but also demonstrated the integration of advanced highway engineering practices with long-term urban planning goals. Its execution underscored the importance of scalable design, phased construction, and resilient materials in modern roadway development. Amid the expansive high desert plains of northern Arizona, the construction of the West Camp Wind Farm emerged as a strategic investment in renewable energy infrastructure. Spanning thousands of acres of open terrain, the project was meticulously engineered to optimize wind capture while minimizing environmental disruption and maximizing grid integration efficiency. The undertaking required a deep coordination of civil, electrical, and structural disciplines, especially given the logistical challenges of transporting and installing massive turbine components in a remote landscape. Site preparation began with extensive meteorological analysis, which had been ongoing for several years using temporary meteorological towers. Data from these towers informed turbine placement by mapping wind patterns, speeds, and turbulence intensity across the site. Once the final layout was approved, access roads were constructed to facilitate the movement of heavy equipment. These roads, typically graded gravel with a geotextile base layer, were designed to handle repeated loads from cranes, trucks, and transport trailers carrying nacelles, blades, and tower segments. Foundation work for each wind turbine involved excavation of large circular pits, generally more than 60 feet in diameter and over 10 feet deep. Soil conditions varied across the site, requiring a combination of mass concrete footings and rock-anchored base plates. After forming and rebar cage placement, concrete was poured and cured under controlled conditions to prevent thermal cracking. Anchor bolt assemblies, precisely set to tight tolerances, were embedded within the foundations to receive the tower base flange. Delivery of turbine components to the site was a carefully orchestrated operation involving specialized transport vehicles and often required temporary modifications to public roads and intersections. Each turbine consisted of multiple tower sections, a nacelle housing the generator and gearbox, and 3 blades often exceeding 150 feet in length. Staging areas were created near each foundation to store components in sequence prior to assembly. Erection of the wind turbines was carried out using high-capacity crawler cranes and assist cranes. The process began with vertical assembly of the tower sections, lifted and bolted sequentially from base to hub height. Crews worked at height using safety harnesses and enclosed platforms. Once the nacelle was lifted into place and secured, the rotor assembly was completed either on the ground and hoisted in a single lift, or blade by blade, depending on wind conditions and crane capacity. Electrical infrastructure was developed in tandem with turbine installation. Each turbine was connected via underground medium voltage cables to pad-mounted transformers, which stepped up voltage for transmission to a central substation. The substation, constructed on a separately graded pad, featured power transformers, circuit breakers, protection relays, and SCADA systems to monitor and control generation output. From there, power was transmitted to the regional grid via a newly constructed overhead transmission line connected to the nearest utility intertie point. Environmental compliance remained a critical aspect throughout construction. Dust control measures, wildlife monitoring, and erosion control systems were maintained, especially during foundation excavation and road grading. Upon completion, disturbed areas were regraded and reseeded with native vegetation to restore habitat. In the rapidly developing entertainment corridor near Glendale, Arizona, the construction of Mattel Adventure Park introduced a highly specialized category of themed development that combines amusement rides with immersive retail and branded environments. This hybrid entertainment venue required a unique convergence of architectural theming, structural engineering for amusement ride systems, and complex mechanical integration to support both indoor and outdoor attractions under Arizona's harsh desert climate. Groundbreaking began with extensive grading and subgrade stabilization as the site demanded precise elevation control to accommodate a mixture of flat ride pads, roller coaster foundations, utility corridors, and pedestrian pathways. Because large sections of the park are enclosed or partially shaded, the foundation systems were designed not only for structural support, but also to accommodate below-slab MEP systems, such as drainage piping, chilled water lines, and conduit for low-voltage systems. A primary engineering focus was the integration of steel-framed ride support systems with the park's architectural envelope. Roller coasters and track-based rides required deep pile foundations and custom fabricated support columns anchored using precision survey controls. Load paths from dynamic forces were modeled using structural analysis software to ensure stability under varying operational and seismic conditions. Coordination between ride manufacturers and local structural engineers was critical to ensure the embedded hardware matched with the prefabricated ride sections delivered to the site. Indoor areas of the park were enclosed with high bay pre-engineered steel buildings, clad in themed architectural facades composed of metal panels, EIFS systems, and specialty coatings to match Mattel's brand aesthetics. HVAC systems for the enclosed attractions were robust, with rooftop air handling units and large ductwork plenum systems distributing conditioned air to maintain interior climate control for both guests and sensitive ride equipment. Utility demands were substantial. Electrical loads included lighting, sound systems, ride controls, food service operations, and administrative zones. A central utility corridor distributed high-capacity power, fiber optics, and water mains throughout the park. Mechanical and electrical rooms were located beneath platform structures and within service corridors, ensuring discrete access for maintenance without interrupting guest flow. Safety and access compliance were integrated from the outset. All platforms, queuing areas, and emergency egress paths were constructed in accordance with amusement ride codes and ADA guidelines. Queue lines were designed with both shade structures and interactive theming elements, requiring coordination between landscape designers, structural engineers, and scenic fabricators. The construction of Mattel Adventure Park ultimately combined the disciplines of industrial ride engineering and commercial construction with creative theming, delivering a facility that supports high daily throughput while withstanding the operational and environmental rigors of the Arizona desert.